So today we're going to be talking about current carrying wires, and we're going to do a problem which is calculating the magnitude and direction of the force, which is the magnetic force, on a straight segment of current carrying wire in a uniform magnetic field. So first of all, we need to know what this means so we can draw a picture of it. So we have a magnetic field, and we're going to have it going into this board. So we're going to draw little X's. And that's our electric field. And we have a wire, which is going to be in blue. And it's at a right angle to the magnetic field. So therefore, when we look at the equation, which is F magnetic equals the magnetic field, which is always measured in Teslas, times the current going through this segment of wire, which is going to be in amps, times the length of the wire, which is going to be in meters. So, and we can use the right-hand rule, which is basically you have the direction of the current. So in this one, I'm going to do it in green, and the direction of the current is going to be going up through the wire. So our thumb, which is going to point in the direction of the current, and then we wrap our fingers around the wire, and that gives us the direction of the magnetic field. So if we can look at this, this way it'd be the direction of the magnetic field is going this way. So it's going around the wire. So in this equation, it tells us that the wire has a 14 amp current passing through it. So we're going to do our current over here is 14 amps, and it tells us that the length of the wire is 2 meters. And it also tells us that it is going through a magnetic field, which is 3.6 times 10 to the negative 4 Teslas, and that's at a right angle. So usually this equation would have a sine theta, so we can insert that. But since the wire is at a 90-degree angle to the magnetic field, our sine theta cancels out because sine of 90 degrees is 1. So now we have F magnetic equals 14 times 2 times 3.6 times 10 to the negative 4. And if we plug that in, I'm just going to put times 3.6 to the negative 4 times 14 times 2. That gives us a force of 0.01008. So our force is 0.01 newtons. And we know that the magnitude of this, or we know that, the direction and the magnitude of this wire, so this is the magnitude of the force. And then we have the direction, which is, we're going to call this north, east, south, and west. So our current and our magnetic field is going to be going to the west because it's pointing this way. And that is how you calculate the current, actually not the current, but the magnitude of the magnetic field, magnitude of the force, and direction of the magnetic field of a current carrying wire.